Okay, we're going to walk through the assembler and compiler. So I made a little tiny compiler for teaching purposes so that you can see how the big one works. Basically what this does is if you enter 1 plus 2 plus 3 times 2, it converts it to 64-bit assembly using a stack machine. So we push 1, push 2, push 3, pop 2 and 3. We pop 2 and 3, add them, push the result. Then we push 2. Then we have 2. Then we pop the result from 2 plus 3 and multiply. Push the result. Then we pop and finally add the 1. We pop the 1 and add that. So let's look at how this works. Compilers have, normally you solve the problem of a compiler by using a lexical analyzer to tokenize it. This means we convert it to either, we take care of the decimal to binary conversion, or whatever you want to call it. So we handle decimal numbers. We strip out white space if it's a space or a carriage return. This lexical analyzer is working on a buffer, just a buffer of bytes, and if it's it strips out carriage return, and it stays in a while loop, and looping through the characters. If it gets a white space, it strips it out. Otherwise, it converts 0 to 9 to a number. Or it returns, so it returns either a number, an operator, or a left or right parenthesis. And the operators are mul, div, add, subtract. And so the critical thing, so we call getS to get a string, then we parse it, then we unassemble, and then we call to get the result. So what did we have? 1 plus 2 times 3 times 4. 1 plus 2 times 3, let's say times 3, whatever. You see it prints the answer right there. So what this calls the code after it makes it. So here's where it parses, and so basically when you parse, either when you get an operator, you either do it right away or you push it and do it later if it's a higher or lower precedence. So this encodes the precedence as a number. So the precedences are a term. That's either like a variable, an integer, or whatever. Then there's mul precedences. Then those are higher precedence than add. Low, I don't know how you want to order it. You can either go up or down. Anyway, and then finally a parenthesis is the lowest precedence, highest number. So we're going to look at how my compiler works on this code. This code is a for loop. It loops to 100 and calls printf and prints the number. There's an L trace which will look at the result of the lexical analyzer. There's a C trace which will just look at the resulting. This is the code that this compiler makes. This is optimized. The earlier one was not optimized. So XOR, so it's using RSI as a register variable. It's checking at the top for less than 100. Then it's calling printf, incrementing, jumping. Anyway, so we're going to look at the optimizer. Starts with a local variable is a negative off the base pointer. So the local variable I is RBP plus -8. Add the 2 and then 0 and then assign. So this pushes a 0 and then it assigns. That's how it does the I equals 0. You see that I equals 0. That's the first thing it does is it codes the address of I, then it codes the 0, then it does an assignment to that address. Then it has a label because we want to come back to this spot. Then we there's I again. This time we dereference I. then we compare it to 100 right here. And if it's less than, we want either a 0 or a 1 for true or false. Is it less than, true or false? If it's 0, if it's false, then we jump ahead to a label. If it's greater than 100, we're done. So we jump ahead. Anyway, otherwise we do a call. From call start to call end is this is the printf that's implied. There's I, adds, dereferences. There's one parameter going to printf. This is a variable parameter count, argument count. There's one argument going to printf. Then we push the address of the format string. This is stored after this function. After the function code, we store the string for %d. And then we call a function, then we add 18, there's three items on the stack, and this is the end of the call. And it's, anyway, so normally I use the version of return in functions that pops the stack. So normally you don't have popping the stack, but in this case we have a variable number on the stack. Anyway, so then what do? We auto increment. This is post postfix plus and then jump. So there's intermediate code. This is not assembly, it's intermediate code, my own stack machine intermediate code. I don't use I don't use a symbol tree, I use a stack intermediate code. Anyway, so after pass 2, it's figured out the types. When you do a compiler, you have to, sometimes if you multiply by a float, you have to convert from float to int. So you got to figure out all the types. So my compiler starts with Lex, which then it goes in and the parser is what calls Lex. So it has to parse all the for statement, the while, and all that. Anyway, and it has to then it handles expressions. It either does the operator or does it later, and it has a little stack to keep track of which operator needs to be done. Anyway, so over here, then finally it goes through these optimization passes, and we're going to look at those in a second. Anyway, so the optimizations, this one, by 0, 1, and 2 have simplified. If you have integer constants, it replaces them. Past 0, 1, and 2, if you have, let's say you have 1 plus 2 or something, then it simplifies it into 3. You don't, and it figures out the types. So it builds up into bigger and bigger instructions. After pass 3, we have figured out the register variable RSI should be used for I, and we're gonna that's the 8 off the base pointer. Anyway, so this is starting to combine them together into arguments. So the argument for so it pops a stack, and then doesn't assign. By pass 4, we've switched over to register variables. Top of the stack is RAX. RSI is the variable I, and starting to do calls and stuff. And pass 5, it's getting bigger and bigger. And then finally on the final passes, it converts to assembly, and it calls it several times, seeing if it can reduce jumps. You see this jump is 1 byte. The first time we did this, we used a bigger byte, and then we saw we could use a smaller byte, so we used a smaller size. So we used a smaller size. So it puts these in line and makes the final assembly code. So let's look at that a little more closely. So the lexical analyzer has a get char that gets one character, feeds it to the lex. The lex function is where we let's see, if we're lexing a string, then we convert \n and etc. If we're doing if we're lexing, we convert integers to we convert digits to numbers, 0 to 9. If it's alphanumeric, we convert that to an identifier. And my lex looks up in the symbol table for keywords and stuff, or identifiers. So anyway, now we in my lex I handle if def, pound define. I handle that in my lexical analyzer. They call that preprocessor. Mine's actually part of my. It's not a separate pass. It's part of my lex. Anyway, pound include is handled. So when it does lex get char for individual characters, then if it runs out of characters, it calls compiler prompt, which is the command line. Mine does just in time or ahead of time. If you're typing at the command line, then it prints the prompt, and then it calls getS to get from the command line. So I have keywords and stuff are loaded in when you start up the compiler. It loads in keywords into the symbol table. Keyword, if, include, define, etc. And it also loads in all opcodes. Opcodes have different formats. So for example, ADC, there's add register memory 8, 16-bit, 32-bit. There's with an immediate or with another register. Anyway, so let's look up ROL. My assembler, you have to specify if it's one argument or two arguments. That's so that in my assembler, we handle we call lex when we're handling a block of assembly, and if it's an identifier, it makes a new label. Otherwise, if it's an opcode, it starts parsing the opcode. If it's an identifier, now if let's see, where's the opcode? If it's an opcode and it has one argument, it parses an argument. The key to lexing is you keep it one ahead. So it's always sitting one ahead, token-wise. It's sitting on the next token when you call lex. Anyway, if it has one argument, it parses the argument. If it has two, it parses another argument. The parse argument for defined byte, this is for defined byte. The assembler has to handle forward references and undefined things. In C you don't have undefined things. In assembler you have things that aren't defined yet. Anyway, so this parses an instruction. It tries the various formats to figure out which one is the shortest number of bytes. So if it can use a 8-bit immediate, it uses that format. Anyway, then here's where it parses the when it stores if you have a number, an expression, it might have undefined, and it has to resolve those. Anyway, here's where it makes a mask for the various argument types to see if it's register memory, immediate, register memory, RAX. It whittles down to figure out which form of the instruction can be used. If there's multiple forms, it tries to see which one is the shortest. That's how it resolves the assembly. So parsing arguments, it has to handle the scaling and SI. Anyway, so the unassembler, we have those opcodes. The critical thing for doing an unassembler is you have to do a comparison. They're multi-bytes, so you have to put them in some kind of order, based even if they're multi-bytes. Once you have an order, then all you have to do is a binary search. Once you have a comparison, so you do a binary search to whittle down which instruction it is, and then you you unassemble all the arguments. Anyway, so when it starts up, it calls this, which stores the precedence, makes a table of precedence, fill-in tables. When you initialize the compiler, it initializes this. It has strings for the various internal intermediate codes. I don't use a symbol tree. I use my stack machine. This tells how many arguments on the stack, etc. If it's a constant, then I have my error messages. I have exception handling, so I can call an exception and print out a message. Anyway, so it loads the symbol tables into the hash. It loads all the keywords into the hash table. This is where it initializes. It calls what we were just looking at. Load the assembler opcode hash tables and keywords. Sometimes, let's see. So we have either ahead of time or just in time. For inline assembly, we have to handle that. For ahead of time assembly, this compile. This is for making a binary file. You have to convert to imports and exports. You have to make a binary file with imports and exports, and you have to save it as a binary. Anyway, I do just-in-time compiling anywhere I want with #DXE. Anyway, we looked at Lex. Here's the expression evaluator. It basically either does it uses a stack and either does it right now or does it later based on the precedence. Statement parser. This is where it goes through all the statements, and if we look at do while, we parse. Let's see. We make a label because we want to loop back. Then we parse one expression, one statement that's either with the block of open brace, end brace. Then we parse a keyword. We parse an expression for the do while, and then we put the labels because we had to forward reference to if the label was false, if the expression was false. Now the code generation, after it parses, it hands it off to be optimized and converted to machine code. So we handle the various optimization passes. There's 0, 1, 2, 0, 1, 2. That's done 3 times. Part 3, 4, 5, 6, and then 7, 8, 9, 10 is done 4 times. It does a little bit more each time. Anyway, so 0, 1, 2, it handles, it's got a big case switch statement for all the intermediate codes. It converts simplifies integers, and it resolves types. That's what it does on this first pass. It also converts, if you have shift, it tries to use the shift operators instead of multiply and divide. Pass 3, this basically it figures out which variables should be registered variables, which offsets off of the base pointer should be registered variables. Sometimes you can't use a register variable because the address has been taken. You can't take the address of a register variable, so that it has to keep a count of how many references and dereferences, and that's how it tells if it can use a register variable. Oh, one more thing with the assembler, it has to handle expressions, and it keeps a count of how many addresses are in an expression. If it's an even number of addresses, like if you take an address of a label minus another label, then it's not a label and it doesn't need an absolute address correction. Now, if you have a label minus a label, it's an integer. If you have a label, it's an absolute address and it needs to be patched. If it's an integer, it doesn't need to be patched. Anyway, so I was just going to tell you that. This pass 3 figures out register variables. Pass 4, I don't remember what it does. Basically, it starts combining them together into bigger and bigger instructions. Oh, we have to convert from the stack machine to register variables too, and we convert to how many parameters. There's up to 3 parameters for one code. If you have move, if you have question mark, colon operator, that takes 3 parameters. So in 7, 8, and 9, we start calling to convert to assembly. We have a little buffer for each stack, and we start making assembly code, and we either mark it, we have to handle type conversions going in or out of the intermediate code, and we convert okay, so we convert to double or convert to int, and then we're making assembly code here. This ICU 16 that says save 16 bytes of 16 bits. So that's assembly code. So this final pass 7, 8, 9, and 10 calls this back, a lot of routines in this back end. This back end is where we do most of the conversion to assembly. So for example, let's see what we got here. Memset, those are inline functions, or modulo, min-max, limit. Those are inline functions. Let's see what we got up here. And branch. So basically it figures out the arguments are either a register, an immediate, or a displacement off of a register, or displacement with index. Those are the so by the time we're done, it doesn't do the stack very much anymore. Anyway, so I think that's, so it's either a register, the arguments are either a register or a or stack, or displacement off a register, or a RIP with the displacement, or SIB is, that means an indexed. So it converts the parameters to each one of these intermediate codes to one of those, and then it anyway, so one of the critical things is by the time it gets into a register, it's been converted to 64-bit. That's how my compiler works. So if it's in a register, it's been converted to 64 bits. When you load and store, that's when it handles smaller sizes or bigger sizes. Anyway, so that's what you need to know. So yeah, that's my assembler, unassembler, compiler. Hope you enjoyed it.